Welcome to Introduction to Geology. I'm Dr. William Patterson. In this module, we will be discussing plate tectonics, the theory that unifies geology. The Earth's rigid outer shell of rock, known as the lithosphere, is broken into about a dozen different plates that slide past, converge with, or separate from each other as they move over the weaker, ductile asthenosphere. Plates are formed where they separate and recycled where they converge in a continuous process of creation and destruction. Continents embedded in the lithosphere drift along with the moving plates like a helpless iceberg. The theory of plate tectonics describes the movements of plates and the forces acting on those plates. It conveniently explains volcanoes, earthquakes, and the distribution of mountain chains, rock assemblages, and structures on the seafloor, all of which result from events at plate boundaries. Plate tectonics, therefore, provides a conceptual framework for much of geology. It's a unifying theory. In the 1960s, a revolution in thinking shook apart the world of geology. For 200 years, geologists have been developing various theories of tectonics, the general term used to describe mountain building, volcanism, earthquakes, and other processes that construct geologic features on the Earth's surface. It was only after the discovery of plate tectonics that a single theory could satisfactorily explain the whole range of geological processes that we observe. The basic ideas of plate tectonics were put together as a unified theory of geology about 60 years ago. The scientific synthesis that led to this discovery of plate tectonics, however, really began much earlier in the 20th century with recognition of evidence for continental drift. But going back further, the idea of continental drift was first stated as such changes in the superficial parts of the globe seem to me unlikely to happen if the Earth were solid to the center. I therefore imagine that the internal parts might be a fluid, more dense and of greater specific gravity than any of the solids we are acquainted with, which therefore might swim in or upon that fluid. Thus, the surface of the Earth would be a shell capable of being broken and disordered by the violent movements of the fluid on which it rested. This was said by Benjamin Franklin in 1782 in a letter to a French geologist. The concept of continental drift, a large-scale movement of continents, has been around for a long time. In the late 16th century and in the 17th century, European scientists noticed the jigsaw puzzle fit of the coasts on both sides of the Atlantic Ocean, as if the Americas, Africa, and Europe had once been part of a single continent that had suddenly been pulled or rifted apart. By the end of the 19th century, the Austrian geologist Edward Suess had put together some of the pieces of the puzzle. He wondered that the present-day southern continents had once formed a single giant continent called Gondwana, or Gondwanaland. In 1915, Alfred Wegener, a German meteorologist, was recovering from wounds suffered in World War I. He wrote a book about the breakup and drift of continents in which he laid out the remarkable similarity of geologic features on opposite sides of the Atlantic Ocean. In the years subsequently, Wegener postulated a supercontinent that he called Pangaea, Greek for all lands, that broke up into the continents we observe today. Although Wegener was correct in asserting that continents had drifted apart, his hypothesis about how fast they were moving and what forces were pushing them across the Earth's surface turned out to be wrong, as we'll see. And those errors reduced his credibility among other scientists. Geologists didn't take a meteorologist seriously. So after about a decade of people yelling at each other, they decided that Wegener was wrong. Wegener, along with other proponents of the drift hypothesis, pointed out that not only did the geography match on both sides of the ocean, but there were also similarities in rock ages and rock types. They also proposed ideas that are accepted now as good evidence of drift, based on fossil and climate data. Fossils of the 300-million-year-old reptile Mesosaurus, a freshwater reptile, have been found in Africa and South America, but nowhere else on Earth. This suggests that the two continents were joined together when Mesosaurus lived, i.e. 300 million years ago. Additionally, the animals and plants on the different continents showed similarities in their evolution until the breakup time. After that, they followed different evolutionary paths because of their isolation and changing environments in the separate locations. Additionally, rocks deposited by glaciers that were present 300 million years ago were found distributed across South America, Africa, India, and Australia. If these southern continents had once been part of Gondwana that was located near the South Pole, a single continental glacier could account for all of these deposits. The geologic evidence didn't convince the skeptics, though, who maintained that continental drift was physically impossible. I worked with a guy in St. Louis once that said, "Well, it's like having a whale in a bathtub. It's physically impossible." And we often wondered what that meant. No one had been able to come up with a plausible driving mechanism that could split Pangaea and move the continents apart. Wegener thought that the continents floated like boats across the solid oceanic crust, dragged along by the tidal forces of the sun and the moon. Yeah, that's a bit of a stretch. His hypothesis was quickly rejected, however, because it could be shown that tidal forces are much too weak to move continents. So that was out. The real scientific breakthrough came when people realized that convection in the Earth's mantle could push and pull continents apart, creating new oceanic crust via the process of seafloor spreading. In 1928, the British geologist Arthur Holmes, no relation to Sherlock, proposed that convection currents dragged the two halves of the original continent apart, with mountain building in the front where the currents are descending and the ocean floor development on the site of the gap where the currents are ascending. Many people still argued, though, that the Earth's crust and mantle are rigid and immobile. Holmes conceded that purely speculative ideas of this kind, specifically invented to match the requirements, can have no scientific value until they acquire support from independent evidence. That independent evidence emerged from the extensive explorations of the seafloor after World War II. Marine geologist Maurice "Doc" Ewing showed that the seafloor of the Atlantic Ocean was made up of young basalt, not old granite, as some geologists had previously thought. Additionally, the mapping of the undersea mountain chain called the Mid-Atlantic Ridge led to the discovery of a deep valley or rift running down its crest. Because most earthquakes are generated by faulting, these results indicated the rift was a tectonically active feature. Other mid-ocean ridges with similar rifts and earthquake activity were subsequently found in the Pacific and Indian Oceans. In the early 1960s, Harry Hess of Princeton and Robert Dietz of the Scripps Institute of Oceanography proposed that Earth's new crust separates along rifts and mid-ocean ridges, and that new crust is formed by the upwelling of hot, molten material into these cracks. The new seafloor, actually the surface of a newly created lithosphere, spreads laterally away from the rifts and is replaced by even newer crust in a continuing process of plate creation. This led to the Great Synthesis, 1963 to 1968. The seafloor spreading hypothesis put forward by Hess and Dietz explained how the continents could move apart through the creation of new lithosphere at mid-ocean ridges. But it raised another question. Could the seafloor and its underlying lithosphere be destroyed by recycling back into Earth's interior? If this is not the case, the Earth's surface area would have to increase over time. The Earth would have to get bigger. And that's not happening. For a while in the early 1960s, some physicists and geologists believed in this idea of an expanding Earth. Other geologists recognized that the seafloor was indeed being recycled. They were convinced this was happening in several regions of intense volcanic earthquake activity around the margins of the Pacific Basin, known collectively as the Ring of Fire. The details of how this worked, though, remained unclear. Then, in 1965, the Canadian geologist J. Tuzo Wilson first described tectonics around the globe in terms of rigid plates moving over the Earth's surface. He characterized three basic types of boundaries where plates move apart, come together, or slide past each other. Soon afterward, other scientists showed that almost all contemporary tectonic deformation, process by which rocks are folded, faulted, sheared, or compressed by tectonic forces, is concentrated at these boundaries. They measured the rates and direction of crustal movements and demonstrated that these movements are mathematically consistent with a system of rigid plates moving over the planet's spherical surface. I once saw this modeled using a shoebox and some strips of colored paper, and it made total sense at the time, but I don't remember how it works. The basic elements of the new theory of plate tectonics were therefore established by the end of 1968. By 1970, the evidence for plate tectonics had become so pervasive that almost all Earth scientists began to love the theory. Textbooks were revised, and specialists began to consider the implications of the new concept for their own fields. According to the theory of plate tectonics, the lithosphere is not a continuous shell, but is broken up into a jigsaw puzzle mosaic of rigid plates that move over the Earth's surface. Each plate travels as a distinct unit riding on the asthenosphere, which is also in motion. The largest is the Pacific Plate, comprising much, though not all, of the Pacific Ocean basin. Some of the plates are named after the continents they include, but in no case is a plate identical with a continent. The North American Plate, for example, extends from the Pacific coast of North America to the middle of the Atlantic Ocean, where it meets the Eurasian and African plates. In addition to the 13 major plates, there are a number of smaller plates. An example of a small plate is the Juan de Fuca Plate, a piece of oceanic lithosphere trapped between the giant Pacific and North American plates, just offshore of the northwestern United States. Others are small continental fragments, such as the Anatolian Plate, which includes much of Turkey. To see plate tectonics in action, you merely have to go to a plate boundary. Depending on which boundary you visit, you may find earthquakes, volcanoes, rising mountains, long narrow rifts, faulting, or folding. Many geologic features develop through the interactions of plates at their boundaries. There are three basic types of plate boundaries, all defined by the direction of movement of the plates relative to one another. At divergent boundaries, plates move apart and new lithosphere is created. Therefore, the plate area increases. At convergent boundaries, plates come together, and one plate is recycled into the mantle or forced down into a slab graveyard, as we'll see later. In this case, the plate area decreases. Finally, at transform faults, plates slide horizontally past one another, and therefore the plate area does not change for either plate. Like many natural models, these three plate boundary types are ideal. There are also oblique boundaries that combine divergence or convergence with some amount of transform faulting. What actually goes on at a plate boundary depends on the type of lithosphere involved, because continental and oceanic lithosphere behave differently. The continental crust is made up of rocks that are both lighter and weaker than those of either the oceanic crust or the mantle beneath the crust. Two of these consequences in mind. One, because continental crust is lighter, it's not as easily recycled back into the mantle as oceanic crust is. Two, because continental crust is weaker, plate boundaries that involve continental crust tend to be more spread out, and thus more complicated than those that involve oceanic crust.
That's all I had to say about that.
Meanwhile, back in the year one, when you belonged to no one, you didn't stand a chance, son.